Take a look up at the board here and tell me what the first thing that comes to your mind is. Area equals impulse. Good. Area equals impulse. We're going to think that every single time we see this graph, right? Every single time. Area equals impulse, area equals delta P. All right. What's the difference between the first area right here, the red one, and then we'll say the black one down here, the first area and the second area? Good. One's positive, one's negative. Which one's positive? The red one is positive. It's above the x-axis. The black one is negative. It's below the x-axis. Good. These shapes are a little bit odd. How do we break these up into the shapes that we need in order to calculate the area of both the top and the bottom one? Rectangles and triangles. So let's draw a line right here. Okay, we've got triangle number one, rectangle number one, and then we've got triangle number two. And then let's draw another one right here. We've got triangle number three, and we've got rectangle number four. What's the equation for the area of a rectangle again? Base times height, good. What's the equation for the area of a triangle? 1/2 base times height, good. Does it need to be a right angle triangle? No, but it doesn't really matter. If you do break it into a couple triangles to make it a right angle triangle, that's fine. Once we get the area, sometimes we've got to do something else with it. One of the most common things that we have to do with it is to find the change in velocity. How do we find the change in velocity after we've done this whole area equals impulse thing? Oliver? What do you mean cross multiplication there? Okay, what equation? Okay. Good, good. M times delta V. Impulse is equal to M times delta V. Now we have the impulse because we can always find that by calculating the area, right? Got the impulse. We've always got that. Now you can set that equal to F times delta T, but that's not very useful usually in these graphs because the force isn't a constant force usually. So it's not really useful. Let's go straight to this, M times delta V. Assuming you've got the mass, then you can calculate delta V. Or if you have delta V, then you could calculate the mass. Make sense? Yep. Yeah, well, yes, that's a good question. When you do all this totaling to find the total area, the total impulse, do you subtract the bottom one from the top one? It's a question if you didn't hear it. Effectively, yes. Okay, I like to think of it as adding. Okay, we add all of the areas, but we're adding a negative value down here. So it's the same thing as subtracting it, yes. Yeah. Let's take a quick look at this, please. Okay, we got a force versus time graph. Okay, it looks like this. Let's say this is 2 seconds. This is 4 seconds. Let's say the impulse is already 20. I want you to tell me what the maximum force is. It's a little bit of a different question than we've been asked so far. But what's the first thing you think when you see this graph? Area equals impulse, right? Take a couple seconds here and see if you can figure this out, remembering that area equals impulse. Just because you're asked for something different than what we're usually asked for doesn't mean the strategy changes. We still got to think area equals impulse right away. So take a couple seconds, keep that in mind, and see what you can do to find the maximum value of the force in this problem here. Okay, who has an answer here for me? What do we think the answer is? Dane was real quick on it, so let's see if he has the right answer. Dane, what do you say? 10. Okay, I heard somebody over here say something different. Anybody have another answer besides 10? I think I heard a 5. Did I hear a 5? Who says 5? Who says 5 is the correct answer? All right, who says 10 is the correct answer? Okay, a few more people say 10 than 5. Let's take a look at it here. We know the area equals the impulse. We still think that, even though we have the area this time, we have the impulse, we still got to use that whole area equals impulse thing. So let's say delta P equals area equals 20. 20 is going to be equal to 1/2 base times height. Let's calculate the height here. Okay, the height is equal to, here, let's just plug some numbers in here. 20 is equal to 1/2 of the base, which is 4, times the height. height ends up being equal to, what's the height equal? Height equals 10. So does that mean that's the maximum force? Yes. Yes, that's it. Okay, I'm a little bit puzzled here where the 5 came. Oh, I know exactly where the 5 came from. People went 20 is equal to base times height, right? Oh, or F times delta T. Yeah, okay. So let's take a look at that. If you said area is equal to base times height, then we would have subbed in 4 for the base, and we would have got 5 for the height, so that would have got us 5. Or if you said impulse is equal to F times T, which is a perfectly valid equation, but we said that you don't use that very often in these F versus T graphs. How come? Why don't we use that very often in these F versus T graphs? What are you calculating there? Not max force. You're calculating the average force. The average force. Now, in this particular case, since it's a nice symmetrical graph, it goes up to 2 seconds and then down to 4 seconds. The maximum force is simply twice the average force. So you can actually do that and figure out the max force that way. Having said that, I wouldn't suggest doing it that way, because if it wasn't a symmetrical graph, if that went up to 2 seconds and then let's say down to 5 seconds, like this, then the average force would not be half of the maximum force. Okay, so the easiest way to do this, the most reliable way to do this, is exactly this way. Get the area, set it equal to 1/2 base times height, and remember the height is going to be the max force. Okay, does that make sense? Now, if you were asked for the average force as opposed to the maximum force, then we would do it exactly the way that you suggested we do it here. Right? If we were asked for the average force. But if we're asked for the max force, in this case, it works to get the average and multiply it by 2. Sometimes it doesn't work to do that. It depends on the shape of the graph. Okay? So let's always just remember this. Max force, average force. All right? All right, let's take a look at some of the questions that we had for homework here now. Let's take a look at page 467, our check and reflect questions, number 1 to 7. Any issues with any of those questions, 1 to 7 on 467? I know that some of you actually did more than you had to do. As I was looking through it, some of you did all the way to 13. That's great. Okay, you're going to have to do that anyways, but it just wasn't homework for today, so we won't go over those ones today. But is there any issues up to number 7, which is what we assigned? For 7? 7 in math one? It is. Yeah, I'm not sure off the top of my head what the answers are. They're in the back of your book, but we can do that if you want. Want to do 7? Okay. Any others? Going once? Going twice? Okay, 7 it is. All right. As soon as we see this, what do we think? What comes to mind the instant we see this graph? Area equals impulse. Good. Now, there's one thing that I want to do here before I go any further, because I just spotted this. Now, you might not spot this right away. Sometimes I don't spot it right away, but I just happen to spot it this time right away. Down on the y-axis here, we've got our time in milliseconds. So I'm going to circle that in red just to remind me to do something with it. When I do a calculation, everything on the x-axis is going to be times 10 to the minus 3. Got it? Now, usually I'll notice that at some point, not always right away. Sometimes I'll miss it entirely. Okay? But whenever it is that you see it, if you see it, then make sure that you circle it just so that you don't forget to deal with that. All right, let's see what the question says. A says, from the graph below, what is the magnitude of the impulse provided to a 48-gram tennis ball? Circle that one as well. 48-gram tennis ball that served due south. The area is equal to the impulse, so let's just find the area of this. The area equals a 1/2 base times height, because it's a triangle. The base goes from 0.5 to 5.5, so the base is 5. Be careful with that, right? Okay, what's the temptation? Oh, it goes all the way up to 5.5. Let's make the base 5.5. It's not, because it doesn't start at 0. So it's 1/2 of 5, the base, times 10 to the minus 3. Let's not forget that. We're less likely to forget it because I've circled it. The height goes to 900. We do our calculation there, 1/2 of 5 times 10 to the minus 3 times 900. 2.25 Newton seconds, or 2.25 kilograms meters per second. Good, there's the impulse. B says, what's the velocity of the ball when the racket and the ball separate? Well, we know that when we want to find the change in velocity of the ball, we're going to say delta P is equal to m times delta V. And presumably, since it's a serve, the initial velocity is 0. And if the initial velocity is 0, then the final velocity, which is actually what we're looking for here, ends up being the same as the change in velocity, which is what you're used to finding. So we know what delta P is here. We know what the mass is. And we're just solving technically for VF, but it ends up being the same thing as delta V. Delta V ends up being delta P over m. It's 2.25 Newton seconds over a mass of, I can say 0.048 kilograms. Or you can simply say 48 times 10 to the minus 3 kilograms. Either one of those works just fine. Let's figure what that is. Do the math, it's 46.9. 46.9 meters per second. Now, technically, it should be south, I guess, because everything in this question is south, right? Who was it that asked me for the answer to that? Right? Did you get the right answer? The milliseconds? Yeah, right here. Yeah, that's such a common mistake, and I'll tell you, it's probably more common on graphs than anything else. The good news is, on graphs, we don't often see strange units like that. Usually they just give us the standard units on graphs, but be aware of it just in case, because I've seen it. And I've seen it on, and I've given it on unit tests, okay, where we have units other than seconds and newtons. All right? The next thing that I want to do here is to take a quick peek at conservation of momentum, which is what we've been doing over the last, the last part of yesterday. Yesterday we said that momentum is conserved, or in other words, momentum stays the same in an isolated system, always. What did that term isolated mean to us? What was an isolated system? A system in which, Jesse? Yeah, there's no outside forces. What that really means is that there's no energy in or out. But the practical implication of that is that there's no outside forces. Because, of course, no outside forces, you can't have energy coming in or out of it without any external forces or without any outside forces. Now, if momentum is conserved, if momentum stays the same in any interaction, any collision or explosion, and again, by an explosion, we don't necessarily mean literally a bomb exploding. We could mean something as simple as standing on ice throwing a ball. Okay, you and the ball were one, you became two. You split apart when you threw that ball. The ball went one way, you went the other way. Okay, if we look at conservation of momentum in any collision or explosion and recognize that momentum stays the same, then every single time we have a collision or explosion, we're going to set it up like this. Pi equals Pf. And then we're going to sub in an expression for Pi and Pf. But what we have to do before we sub in an expression is to count the number of objects we have, both before and after. How many objects do we have before this collision or explosion has taken place? How many objects do we have after this collision or explosion has taken place? For each object that we have to sub in this term m times v. mv is the momentum of an object. So for each object with momentum, there has to be an mv. It may look like this, m1v1i plus m2v2i equals mvf. If that's the case, can you tell me how many objects I must have had in the question before the collision took place? 2. Good. How many objects do I have after the collision takes place? 1. So in other words, they stuck together. Okay, it's two cars coming together, and they crash into each other, and they entangle. They stick together as one. Okay, 2 objects become 1. Maybe we see something like this. Maybe we see something like 0 is equal to m1v1f plus m2v2f. How many objects did we have before the collision this time? 0 objects? Not necessarily. All we know is that there was 0 momentum. So it was probably 1 object that just wasn't moving, right? If you'd rather write that in as mvi, and vi becomes 0, that's okay. Or if you just recognize that it's 0, just plug in the value of 0 for it. How many objects do we have after this event has taken place? 2. So probably 1 object with 0 momentum has become 2. What's the situation here, a collision or explosion? 1 thing has become 2. They go off in opposite directions. It's an explosion, right? Just be prepared for any scenario. Okay, we know that this step is the same in all of them. This step is different depending upon the problem, depending upon how many objects we have before and after. Let's take a look at the 2 questions we had for homework last night on page 477. I know we're going to have to go over one or both of these just because of taking a look at your homework earlier. Pretty sure 2 was one that I saw that some people struggled with. How are we for number 1? Good? Can we go over number 1? Sure. Let's go over both of them here. Number 1 says a student on a skateboard with a combined mass of 78.2 kilograms is moving east at 1.6 meters per second. So let's look at this as a mass, and let's look at this as a velocity. This student and the skateboard are going together as one object, okay, as one, before anything has taken place. So there is only going to be 1 object before the event has taken place, or at least so far. As he goes by, the student skillfully scoops up a 6.4 kilogram backpack from the bench where he had left it. So he's skateboarding. He picks up a backpack, and then him and the skateboard and the backpack go off as one. How many objects did we have before the event takes place? Okay, before he picks up the backpack, how many objects do we have? There's actually 2, isn't there? There's the backpack, there's the skateboarder and the skateboard himself. That's M1, V1, I. This is going to be M1. This is going to be V1I. Plus the mass of the backpack, M2, times V2I. What's the value of V2I? 0, right? Because the backpack is sitting at rest on the bench. Now, after the skateboarder, the kid, and the skateboard itself and the backpack go off, how many objects are there now? There's 1, right? The kid and the skateboard and the backpack act as 1 object. They all go off together. So what are we going to write here? Just MVF. Let's not call it M1 V1F or M3 V3F. It's all of them, right? It's the whole mass combined. And we're looking for VF here. All right, M1 is 78.2 kilograms, 1.6 meters per second. Just going to cross this off. Why did I do that? Because it equals 0. V1I is 0, so there's no reason why I can't just cross that off. If you want to put in the values for it, then that's fine. But there's no need to do that when we know right away that it's 0. Now, what's the total mass here? 78.2 plus 6.4, 84.6. This is what the mass of the object, the 1 object, is after the collision's taken place. We multiply that by VF. 78.2 times 1.6, divide that by 84.6, should give us 1.5 meters per second. And since everything was east, the final velocity is going to be to the east as well. The guy was going 1.6 meters per second. He slowed down after he picked up the backpack. Not dramatically, but he still slowed down after he picked up the backpack. Why? Not because he stuck his foot out and slowed himself down, or however you skateboarders slow down on a skateboard. But why did he slow down? Because his mass increased, right? He had a mass of 78.2. He now has a mass of 84.6. His mass didn't increase dramatically, which is the reason why the velocity didn't decrease dramatically, but it still decreased. All right? Today, is that okay? That makes sense? Number 2 says a 1,050 kilogram car at an intersection has a velocity of 2.65 to the north. The car hits the rear of a stationary truck, and then their bumpers lock together. So how many objects do we have before this collision has taken place? There's 2. Okay, we're going to call this one M1. This one's going to be what? V1 or V2? V1, yes. V1I or V1F? V1I, good. The other object, the truck, okay, sorry, that's an F. I said I, but the truck, we don't know what the mass of the truck is. We're going to call that M2, okay, whatever it is what we're looking for. Okay, but we do know that V2I is 0 because the truck was at rest at the stop sign. And we know that, we got another velocity here. What's this going to be? VF, not V1F, not V2F. They're going off as one object after the collision. So we're just going to call it VF. All right, how many objects do we have before this collision has taken place? 2. So it's going to be M1 V1I plus M2 V2I equals how many objects after? 1. So it's going to be MVF. This we can cross off again because the velocity of the truck was 0. M1 is 1,050 times 2.65 equals, what's the total mass? Yeah, we don't know what it is, right? So what do we do, Paige? It's 1,050 plus M2, right? What I'm going to do, I think, is just leave it as M right now. Let's calculate the total mass and then subtract. Right? There's no difference in what you're going to get for an answer, but I think it just looks a little easier when we have one M in there as opposed to 1,050 plus M, if that makes sense. Okay, there's no reason why you can't do it that way if you're good with math. VF is 0.78. What does M equal there, the total mass? What is it? 3567.307, thank you. Now, that's not the mass of the truck. That's the total mass. We're going to get the mass of the truck, which is M2, by subtracting 3,567.307 minus 1,050. And I presume when we do that, we get 2.5 times 10 to the 3 to the right number of digits. Good? How many people got that number? How many people got that answer? All right, good. How many people did it my way here and solved for M and then subtracted it? Okay, and how many people put in, instead of putting M in there for the total mass, how many people actually replaced 1,050 plus M2 in there for it? Okay, just one. Okay, mathematically, I think that's a little bit harder. Not much, but a little bit harder. But it's absolutely just as correct. Okay, you end up having to do the same thing in the end. Is that okay? All right. Let's take a look at 9.7 here on page 478. Does a basketball player in her wheelchair, player A, have a combined mass of 58 kilograms? She's moving at 0.6 meters per second and pushes off a stationary player while jockeying for position near the basket. Player A ends up moving at 0.2 to the west. So we've got a couple of different directions here now. It's especially important when we're dealing with a couple of different directions that we define something as positive and something as negative. Probably makes sense to go east positive. That's usually what we do. The combined mass of player B in the wheelchair is 85. What's player B's velocity immediately after the interaction? All right. How many players do we have before this collision has taken place? Okay, it's how many? There's two, right? One of them's at rest, but there's two objects, right? Let's call this M1. We could call it MA if we wanted to, but I don't like letters for subscripts for some reason. I like numbers, so I'm going to call it M1. This is going to be what? V1, V1I or V1F? V1I. Yeah. Pushes off a stationary player, player B. Player B, we're going to call M2. Her mass is 85 kilograms, and her initial velocity, we're going to call it V2I, is 0. Player A ends up moving at 0.20 meters per second to the west. We're going to call that V what? VF, yes. V1F or V2F? V1F, yes. V1F. Now, just caught this. I'm going to circle that west to remind me that it's opposite to the direction that the player was going before. We want to find V2F. Oh, would you look at this? Scroll down to the diagram and the givens are already written down for me. Didn't even notice that. It's okay, we need to go through that process anyways. Are these givens okay? Honestly, that's probably about the toughest thing to do in these conservation momentum problems is identify these givens. Once you've done that, then usually the problem ends up being fairly simple once you've got the givens identified correctly. Yep. Well, they are apart. They don't stick together. Okay, so we're going to use the same masses. Yeah, they're not losing weight or anything in that process, or they're not gaining because they're not combining, right? They're not sticking together. All right, let's say Pi equals Pf. There were two objects before the collision, although, as Oliver pointed out, one of those objects wasn't moving. So if you wanted to, you could have considered there to be only one object. That would work. How many objects are there after the collision? How many? 2. So we're going to say M1 V1 F plus M2 V2 F. Cross that off, like Oliver said, because there's no velocity before the collision. M1 is 58. V1I is 0.60. M1 is 58. V1F is negative 0.20. Don't forget the negative. We have it circled, so that helps us to remember, but just pay attention to it. M2 is 85 times V2F. Let's calculate this. Let's say 58 times 0.6. That's going to give us 34.8 on the left-hand side. Now let's add to that. Pay really close attention to this. 58 times 0.2. Why did I add that to it? It becomes a negative. 58 times 0.2 is a negative, times negative 0.2 is a negative value. How do I get it to the other side? I add a negative value to the other side, right? So it becomes whatever I get on the left-hand side plus 58 times 0.2. I'm going to press equals now, and then I'm going to divide that by 85. I end up getting a velocity of 0.55. And it does work out to be a positive value. So what does that mean about direction? It's going to the east, yeah. Good? It's a little bit harder than the questions we had yesterday, right? But just a little bit. It's the same basic process that we go through. You look at all your givens, identify how many objects you have before and after, and then set it up the same way. It's just that the second step, the substitution of the expressions in for PI and PF, looks a tiny bit different, that's all. All right, let's see what you can do with the practice problems on page 478 that go along with that example problem, please. All right, let's take a look at another example here. We get two football players this time. A Stampeders football player who's 110 kilograms, and he's moving east at 1.8. And he's struck by a 140 kilogram Eskimo defensive lineman moving west at 1.5. We've got a couple of different directions here. So right away, we're probably going to say east is positive. That means west is negative. The fullback is bounced west at 0.250 meters per second. What's the velocity of the Eskimos defensive lineman just before impact? These are a mouthful. Hey, these questions, there's so much wording to them that they just become tricky sometimes because of that, because of the wording. Let's call the Calgary Stampeders player the player number 1. So let's say that therefore this is mass number 1 and this is going to be mass number 2. Right? The Stampeders fullback is object number 1. The Eskimos defensive lineman is object number 2. Who's a football player here? Who plays football? Yes? When you don't have a broken wrist? Do you? Okay. Dane, how does it feel to be treated like an object? Object number 1 and object number 2 are our football players here. So object number 1 and object number 2, the Stampeders player and the Eskimos player. We got a velocity right here. We're going to call that what? V1 or V2? V1 or V2? Feel like the eye doctor. You go to the eye doctor. Do you see this one better or this one? 1 or 2? 1 or 2? One time I went to the eye doctor, and she says, 1 or 2? She keeps going back and forth, 1 or 2, and I'm like, I don't see either one of them. I don't see anything. I'm getting all scared because I'm going blind or something, and then she laughs. Oh, I forgot to put the slide up. Then she put it up, and I could see, well, kind of see at least after she put the slide up. Is this 1 or 2? Is this the velocity of the Stampeders player or the Eskimos player? It's a Stampeders player, so it's V1. But is it V1I or V1F? The initial velocity of him or the final velocity? It's going to be the initial velocity. Good. Struck by the defensive lineman moving west at 1.5. We're going to say that that's going to be V2 because that's the Eskimos player, but that's going to be V2I or F. That's how fast the Eskimos player is moving before the collision. Let's circle that west to remind us that that's going to be a negative value, right? Because it's to the west. And we don't want to forget that. The fullback is bounced west. The fullback is a Stampeders player, so we're going to call that V1. All right, that's the player, the velocity of the Stampeders player, player 1. Is it going to be V1I or V1F? Initial or final? Today? Final. That's how fast he's moving after the collision's taken place. We're also going to circle that in red because that's after the collision has taken place. Or sorry, because it's west, and we got to make it a negative value. We're looking for the velocity of the defensive lineman just after impact. We're looking for V2F. So let's set it up. PI is equal to PF. PI is M1 V1I plus M2 V2I. How come I had two terms? How come I had two terms there? M1 V1I plus M2 V2I. Because there's two players, there's two objects. After the collision has taken place, it's going to be M1 V1F. plus m2 v2f. And we have two objects there, so we're going to have two terms there as well. Let's plug in some numbers here. m1 is 110. v1i is 1.8. m2 is 140. v2i is negative 1.5. Don't forget the negative. We circled it in red to remind us, but be careful about that. v1f is negative 0.25 plus 140 times v2f. So we got a bunch of numbers in there that we got to deal with. Solve for v2f. Pay close attention to this. I'm going to go through the whole process again. We're going to say 110 times 1.8. And then I'm going to subtract 140 times 1.5. Why did I do that? Why did I subtract 140 times 1.5? Doesn't it say there that we're adding them, Jesse? Becomes a negative when I multiply them together. So it's just easier to put it into my calculator this way. The left-hand side is negative 12. Now, I'm going to add to that 110 times 0.25. Why did I add that? Abby? Yeah, on the right-hand side, 110 times negative 0.25 is a negative value. Take it to the left side by adding. Now all I'm left with on the right-hand side is the 140 v2f. Let's divide that by 140, and I get 0.111. v2f is 0.111 meters per second. And it came out to be a positive value, so that means it should be to the east. Is that okay? Brayden, does that make sense? Good? Really, it's the same as the other questions we've done, isn't it? It looks a tiny bit different only because we have two objects hitting each other that were both moving and bouncing apart, and they're still both moving, as opposed to the last question where one of them was stationary before they hit. Okay, and as opposed to the one before that where they hit each other and then they stuck together. Okay, but it doesn't really change how we think about the question. It just changes how it looks ever so slightly. Instead of having one object or whatever, we've had two objects both before and after. All right, your homework is to finish the questions, the last set of practice problems, if you haven't already, and to finish the practice problems on page 479, please. So practice problems on page 478 and page 479.